2A. The population, okay, we have the original population for numbers 1, 2, 3, 4. And again, this 2A is like a duplication of the question 1A. You calculate the population mean and variance and standard deviation. You can simply copy the result over from 1A. So I just copy everything over. So nothing new here. Just for completion, I had this question to duplicate the answer from 1A. So there's nothing new. Now, for 2B, take all possible samples of site 3 by sampling with replacement. Okay, so you take 3 numbers and form a sample. But the way you take it is that you first take the first value, write it down what it is. Then you replace this number back into the pool, and you draw the second value, and you write down what you get the second time. After that, you place that number again back into the pool, and you draw the third value. Then you write down what you get the first time. These 3 numbers constitute one sample. And you just do this repeatedly until you exhaust all possible combinations of 3 numbers. Could it be 1, 1, 2, 3, 1, 2, 1, 2, 3, 3, 2, 1, so on and so forth until you exhaust all possible combinations. Okay, so you're gonna theoretically you're gonna have 64 possible combinations of three numbers from all possible from this population of 4 numbers. And this is a table that give you all these possible samples that come with 3 numbers. Now, this is 64 all possible samples of site 3. You can really see all the possible combinations of 3 numbers: 111, 112, 113, 114, 121, 122, 123. Altogether, you have 64. So 64 all possible samples of size 3. Okay. The question is now you need to calculate the sample mean. You need to calculate the sample means. 111, 1 plus 1 plus 1 is 3 divided by 3, and that gives you sample mean 1. So that's easy. For the second sample, 1 plus 1 plus 2 is 4. 4 divided by 3 is 1.33. So sample mean for the second sample is 1.33. For the third sample, 1 plus 1 plus 3 is 5. 5 divided by 3, sample means 1.67. You just do this to all samples. So you calculate all sample means, and that's you obtain all the sample means. So you obtain the 64 sample means. Okay. Then next question. You tabulate the frequency distribution of the 64 sample means. What we mean here is that okay, you come here. See, these are the 64 sample means. Okay. Now let's see. In this table, I have all these values of sample means. Sample mean 1, sample mean 1.33, sample mean 1.67, sample mean 2, sample mean 2.33, so on and so forth. Now, 1, this sample mean occurred how many times? Let's go back to count. Of all the sample means, 1 occurred only once. So frequency is 1. 1.33 occurred how many times? 1.33 1 time, 2 times, 3 times. I think that's it. So 1.33 occurred 3 times. 1.67, let's go back to count again. 1.67, 1 time, 2, 3, 4, 5, 6. 1.67 occurred 6 times. Occurred six times. So you just do this. So you can do this at home yourself too, until you count all the frequencies for all different sample means. So in the end, you should obtain something like this, and that gave you the frequencies for sample mean distribution. So we tabulate sample mean frequency distribution. Okay. Then draw a bar chart of the frequency distribution of the 64 sample means. Already complete this, and there's no need to demonstrate how to do it. You can do it at home, either using any kind of computer software, either using manually. But make sure that all the bars are not adjacent to each other. Again, this is a symmetrical distribution. Okay. Compare with for the population, which is uniform flat distribution, and this is symmetrical distribution. Now treat the 64 sample means that we just calculated in question 2a as a population. We calculate the mean of the sample means, the variance of sample means, and the standard error, as we did earlier on. And in 1e, you already know how to do the calculation when you have 16 sample means. But here we have 64 sample means, but we are going to do the very similar calculation, but just now we involve a lot more numbers, a lot more values. So you need to have some patience and take enough sheets and give you plenty of time to do the calculation. I do not write out the calculation in details here. I just show you the result, but you need to verify this result through your own calculation at home. Okay? So the mean of the sample mean, if you complete the calculation correctly, it should be 2.5. The variance of the sample means 0.417, and the standard error should be 0.65. So if your calculations are correctly, they should be something like this. Okay? And make sure you verify these results through your own calculations. Okay. Now, 2f, what is the numerical relationship between the mean, variance, and standard deviation of the population results that you obtain in 2a on the one hand, and the mean of the sample means, variance of sample means, and the standard error obtained in 2a on the other hand? Okay. We did the similar thing in 1f. Now, let's first lay out the two sets of values here. We have the mean for the population, which is 2.5. We also just calculated the mean of the sample means is 2.5. Then we also calculate the variance of the population, which is 1.25. And for this all the possible samples of size 3, we just calculate the variance of sample means at 0.417. And for standard deviation for the population is 1.12. And for the standard error, or the standard deviation of the sample mean, we just calculate number 0.65. Now, we are going to study the numerical relationship between these two sets of values, between the population mean and the mean of the sample means, between the population variance and the variance of the sample means, and between the population standard deviation and the standard error of the sample means. First, let's look at between these two sets of values. Again, it's very easy to find out how they are related to each other. They are the same, identical. Okay, so the population mean equals the mean of the sample mean. Now, between the population variance 1.25 and the variance of the sample means, what's going on here? What's going on here? Well, if you use 1.25 divided by 3, you should obtain this value. 1.25 divided by 3, you should obtain 0.147. What is the 3 here? What is the 3 here? The 3, the hint here, look at the hint. For the variance of sample means and standard error, consider 3 the sample size. The 3 is sample size. So this relationship really tells us that if you use the population variance divided by the sample size, you should obtain the variance of sample mean. What about this? Population standard deviation 1.12. How is that number related to 0.65, the standard error? If you use 1.12 divided by the square root of 3, that should give you 0.65. Again, what is the 3? 3 is the sample size, the square root of sample size. So if you use the population standard deviation divided by the square root of sample size, that should give you the standard error of the sample mean. So this, again, is what we call very important numerical relationship between the population mean variance and standard deviation on the one hand, and the mean variance and the standard error for the sample mean on the other hand. Okay. So this is one more time we use all the possible samples of set 3 to reach the very similar conclusion regarding the relationship between the population mean and the mean of the sample means, between the population variance and the variance of the sample means, and between the population standard deviation and standard error of the sample means. So we arrived at the same conclusion, same relationship between these two sets of values by using two examples. All the possible samples of size 2, one time, question number 1, and all possible samples of size 3. In both times, we arrived at the same conclusions in terms of the relationship between the two sets of values. Okay. Question number 3. How do the variance of the sample mean and standard error obtained in 1E compare with the variance of the sample means and standard error obtained in 2E? In other words, do you see any pattern? You know, in two questions, we use samples of different sizes. We use samples of different sizes. Okay. For variance of the sample means, the first time, in first question, the sample size is 2, and the variance of the sample mean is 0.625. For the second questions, sample size is 3, and that gives us a variance of the sample means 0.417. What's going on? See, sample size changed from 2 to 3. The variance of the sample means changed from 0.625 to 0.417. Now, the standard error for the first question, sample size is 2, the standard error is 0.79. The second question, when the sample size raised to 3, the standard error dropped to 0.65. So every time when we increase the sample size, the variance of the sample means decline in value. Standard error also reduced in value. Why that happened? Why that happened? Look at this. We said previously, if you use population variance divided by the sample size, you would obtain the variance of the sample means. If the population variance is given, if the number on the top does not change, you increase the sample size, whole ratio will become smaller. Make sense? So that's exactly when you increase the sample size from 2 to 3, the whole ratio, the variance of the sample means, will become smaller. That's exactly what's happening. Same way, we know the standard error is calculated by using the population standard deviation divided by the square root of sample size. Again, if the population standard deviation does not change, the number values at the bottom become larger, and then whole ratio will become small, and that's exactly what happened. Now, what is the variance of the sample means? What is the standard error of the sample means? Variance, standard errors of sample means are referring to the variations around the mean. When you come to use a sample mean to estimate the population mean, you want the estimation as accurate as possible, right? You do not want this increase. You do not want the estimation has large variations. So you want the variations around the mean as smaller as possible. And that means that the estimation is more accurate. It's closer to the true mean. So you want the estimation to be accurate. Therefore, you want to reduce the variance. You want to reduce the standard error. How do you do that? We just see this here. If you increase the sample size, the variance or the standard error will reduce. So one sure way to increase accuracy in your estimation is to use larger sample size. When the sample size is larger, you have more information, the standard error or the variance becomes smaller, and therefore the estimation is more accurate. So that's is one important conclusion, right? Okay, I'd like to summarize a few important things that we learned from this in-class activity, also along with the reading material, all those chapters. First, we look at this. We have a population that is not is flat, not normal distribution. It's flat, uniform distribution. But from this population, we take all possible samples of size 2, and that's and then this is the sample mean distribution, and bottom left that demonstrate a symmetrical distribution. And but if we increase sample size, we have obtained all samples of size 3, and this is the distribution of all sample means of size 3. It is also symmetrical, and it's closer to a normal distribution, and that is one consequence. When you increase the sample size, that would make the distribution of sample mean closer to a normal distribution, even if the original population is nowhere near a normal distribution. Okay, so that is really a striking result here. Another thing we learned from this in-class activity is the relationship between the the two sets of values. For the population is the mean, variance, and standard deviation on the one hand, and also for the sum of means is means, variance, and standard deviation on the other hand. We know that between these two sets of values, there's a relationship there, right? The population mean is equal to the mean of the sample means, the population variance divided by the sample size equal to the variance of the sample means, and the population standard deviation divided by the square root of sample size equal to the standard error of the sample means. This is the result we obtained by using all samples of size 2. And the same result can be obtained by using all the samples of size 3. Obtain similar conclusions. The mean of the population is equal to the mean of the sample means. The variance of the population divided by the sample size equal to the variance of sample means, and population standard deviation divided by the square root of sample size equal to the standard error of the sample means. And we can summarize this as the general relationship here. Here we use some notations here. We have learned notation that we learned before about the population. Population mean, population variance, and the population standard deviation. Now we introduce this set of new notations for sample means. This is the mean of sample means. So the mu sub m. M here obviously means sample means. The mean of sample means. Now here, sigma sub m raised to the second power. So this is the variance of the sample means. Variance of the sample means. And its square root is sigma sub m, is the standard error. Standard error. So this is a set of new notations to represent the mean of a sample means, the variance of the sample means, and the standard error of the sample means. And how these two sets of values relate to each other. The population mean equals to the mean of sample means, that is represented by this, the mean of sample mean, population mean equal to the mean of the sample mean. Then between these two values, the population variance divided by the sample size equal to the variance of the sample mean. And this is represented by this notation. Population variance divided by sample size n equal to the variance of the sample mean. And finally, the population standard deviation divided by the square root of sample size equal to the standard error. And this is a notation that we can use to express population standard deviation divided by the square root of sample size equal to the standard error of the sample means. Okay. From this formula, you can really see that when n become larger and larger, this value will become smaller, smaller. Same way, when n become larger and larger, this value, the standard error, will become smaller, smaller. Okay. So these relationships will be summarized in the study of the central limit theorem. Actually, the whole in-class activity is designed to prepare you for the central limit theorem. I hope this helps. I see you next time. Goodbye.